Welcome to today's DGAL. My name's Marina Costello and I'm the Mineral Systems Branch Head. We work across and recognise the lands of traditional owners and custodians throughout Australia. As we travel, we listen, learn and share respectfully. Acknowledging First Nations people, continuing connection to land, waters and community helps us understand the importance of land, waters and community. We pay our respects to the people, the cultures and the elders, past and present. Well, today is the second Distinguished Geoscience Lecture for 2025. July already, can you believe it? The Distinguished Geoscience Australia Lecture Series, or DGALs, are a series of presentations nominated by Geoscience Australia staff as a prestigious recognition of their major achievements and contributions to earth science. Today, Jack McCubbin and Philip Wynne from the Mineral Systems Branch will explain how the Australian Fundamental Gravity Network contributes to a national and regional data set, as well as what the future holds as far as gravity is concerned. Let me tell you a little bit about our speakers. Jack has worked on the collection of nationwide airborne gravity in New Zealand, producing a new series of national gravity grids and a new quasi-geoid model. Moving to Australia, he worked on the development of a new Australian quasi-geoid at Curtin University. At Geoscience Australia, he has refined the quasi-geoid and worked in the geodetic absolute gravity program. This year, Jack's moved into our resources area and is leading the AFGN uplift. Jack was awarded a PhD in geophysics from Victoria University in Wellington in 2016. Philip has worked with the gravity team at Geoscience Australia for over 30 years. During that time, he spent several years acquiring gravity data or managing others to do so and managing the National Gravity Database. He's worked on many field campaigns supporting the expansion and maintenance of the AFGN, which is taking him across Australia from every capital city to very remote locations. Last year, Philip was awarded the Australian Society of Exploration Geophysicists Distinguished Service Award, which is a huge honour. So please help me welcome Jack and then Phil to the stage.
So good morning everybody. Today me and Phil are going to talk about the Australian Fundamental Gravity Network and what we're doing to strengthen it for kind of future use under RAPI. Love that. So for most practical purposes, the Earth can be modelled as a perfect sphere with a constant gravity value of 9.8 meters per second squared. It's the value we learn at school, and it can be used for simple mechanics problems like estimating how far a ball might go if you gave it a good kick. But the Earth rotates, which means it spreads out at the equator and has an ellipsoidal shape. And this causes gravity variations across its surface of around 1%. Stronger at the poles where we're closer to the centre of mass, and weaker at the equator where we're further away. So by taking this into account, our kind of spherical chickens in a vacuum physics approximations can be improved. And we can see here that our estimates change depending on where we are by about 50 centimeters. When we delve a little bit deeper, we can look at the Earth's gravity field at even narrower scales and see significantly smaller structures. These variations are mostly due to the highs and lows of the topography and seabed, as well as changes in the density of the rocks and voids beneath the surface. These aren't really variations that we can feel as we walk around or go about our everyday, but they are something that we can measure very accurately with instruments called gravimeters. And they're really important for an incredible range of earth science applications and play a supporting role in a very broad sweep of the work done at Geoscience Australia. My name's Jack McCubbin, and I'm joined by my colleague Phil Wynne. And in putting this together, we've had a lot of support from Wayne and Roger too, of course. Together, we're a quartet of gravimeticians, and in We're in GAPS in the Mineral Systems branch of MEG at Geoscience Australia. And yeah, today we're here to talk about the Australian Fundamental Gravity Network and how we support continental scale gravity mapping across the Australian region. This is all work that's being done under the Resourcing Australia's Prosperity Initiative, or RAPI, which is a $3.4 billion investment over 35 years to secure our future as a global supplier for resources supporting the transition to net zero. By 2032, we will deliver an updated realization of the Australian Fundamental Gravity Network, which is something that sits in the background at the kind of the very start of the national gravity data supply chain, providing a backbone for Australia's regional and continental scale gravity mapping, and supporting a crucial role in much of the science behind RAPI objectives, from groundwater to geological storage assessments, along with a host of other downstream applications. So let's dive in. So this first section is on measuring gravity, or more specifically, why measuring fractions of a percent of gravity matters, as well as GA's role and national impact, and the drive for a more kind of robust and future-proof gravity datum as realized by the Australian Fundamental Gravity Network. When we work with gravity, the basic currency is kind of a residual. It's the part of the signal that's left over after we subtract everything we already understand or can model to show us what we don't or can't. So starting with kind of a raw field, which is sort of shown on the left there, geophysicists will strip away known effects, things like that global ellipsoidal shape, the effect of topography and seawater and more, to produce a kind of residual on the right there. What's left kind of lets us peer beneath the surface and highlights hidden density contrasts in the rocks below. And the range of uses for these kind of residual gravity data is quite remarkable, especially when they're combined with other data sets. They can be used to delineate major crustal boundaries. They aid in the discovery of mineral deposits and so underpin the planning and development of new mines. They can help define the shape and size and structure of groundwater systems, and more broadly feed into geological mapping, from helping define the boundary of large geological building blocks to more targeted applications like spotting salt domes for hydrogen storage. Tiny gravity variations aren't just for geophysicists either. They also sit at the heart of geodesy, positioning, and navigation. We use gravity data to refine global models of the geoid to provide kind of more precise regional models. And these are the height reference surface that turns a GPS reading into a true height above sea level. And accurate heights drive everything from mapping water flow for flood risk assessments and climate change studies, to designing roads and pipelines, to supporting calculations of the safe underkeel clearance for ships. And in fact, tightening these underkeel clearance models in particular by just 10 centimeters can net hundreds of millions of dollars a year in exports. Gravity data, albeit the very broad features, also feed into precise satellite orbit modeling, so improving those GPS positions themselves, and in other work that depends on precise satellite orbits. In short, high-quality gravity data underpin a huge slice of our economic, social, and environmental decision-making. So while some areas still need finer resolution or fresher or newer gravity data, Australia holds what is arguably the world's most complete and internally consistent continental scale onshore gravity data set. And it lets us render really striking images like this. GA's current national database contains almost 2 million gravity stations from thousands of surveys collected over the last 70 years. And we released this as a free pre-competitive data set to give explorers a cost-saving first kind of glimpse at the subsurface. Early nationwide mapping in the 1960s and 70s laid the groundwork and left us with an average of 11 kilometers station spacing. And since then, states and industry have filled the gaps with high resolution data, from 1 kilometer resolution down to a few hundred meters in kind of a piecemeal way. most of which now sits in the National Scale Archive. Nearly all of these readings come from compact relative gravimeters, which is shown in the bottom left there. And these are kind of shoebox-sized devices that measure differences in gravity between sites by measuring the extension and contraction of a spring. They can be used to make local maps of how gravity varies in a kind of a local area. And we make it possible for every one of these local relative gravity surveys to knit together across the continent by providing absolute gravity anchor points. So to put this in context, a joke I often hear when people first learn that gravity varies is, does that mean I will weigh less in some places than others? But the answer to that is actually sort of. It really depends on where you calibrate or tear your weighing scales. If you were to set your scale to 0 before stepping on in, say, Hobart, and then travel with that weighing scale to Darwin, and then step on again, you might find that the reading says you weigh about 0.25% lighter. And this is mostly due to gravity decreasing as you move towards the equator, because of the effects of the Earth spinning that we mentioned at the start. So these relative gravity meters are much like a weighing scale. But we know for sure that the weight inside is in fact not changing. So any variations in the readings as we travel around with it must be due to a change in local gravity. We provide common anchor points for people to tear their scales at, or kind of work out the baseline of their gravimeter, which we call the Australian Fundamental Gravity Network, or AFGN. And they're the orange dots on the map there. At each site, we've installed a permanent marker, normally a brass disc or a small pin, and measured gravity itself, not just how it changes, directly above it with an absolute gravimeter, which is normally a kind of washing machine-sized instrument like GA's A10, which is shown there. More than 1,000 AFGN marks are used to anchor the entire national data set of relative gravity measurements together. And without it, individual relative gravity surveys would be disjoint and independent, and we couldn't map them as a kind of a composite image like what's shown there. The AFGN helps users align their data with existing pre-competitive gravity data products, and it makes large-scale gravity mapping applications possible. And in a moment, I'll hand over to Phil, who will pick up the story about how the network has grown over time and a few more details about the A10. But before I pass the baton, I'd just like to make one final point. The AFGN is built around physical infrastructure in the form of those markers on the ground, but also in the sense that it relies on sites to be stable and not changing over time. Unfortunately, roadworks, new buildings, and other ground disturbances slowly take their toll, and marks vanish. And as they do, crews running relative gravity surveys have to travel further for the next nearest intact site to tie their relative gravity measurements into the network. This process requires 2 return trips in a single day, and once station spacing between usable marks stretches beyond about 200 kilometers, tying surveys into the network becomes a real logistical headache. So to keep everyone informed, by default, we now present each mark's health in the public AFGN portal, which I'm showing there. Green and blue circles are the good or okay sites, and everything else is destroyed or has an unknown status. Until recently, there were fewer than 200 or more of the 1,000 marks total, and yeah, we're doing some work to rectify that and revitalize the network. So I'll just hand over to Phil now and then come back to explain how the RAP initiative will uplift the existing network and kind of future-proof our methods.
Thank you, Jack. Good morning, everyone. I'm going to go through the history and growth of the AFGN and also talk about some of the issues we have, and then go on to describe the A10 and how it works. My apologies, I've got to go the right way. So the AFGN is about 75 years old, started in 1950 with one of the stations you can see here. Our last survey was in 2023, and you can see the A10 in action. But of course, we aren't the only people that have worked on the AFGN. There have been a lot of people over the years, such as these in the list you could see. And we've also got to thank the state and NT geological surveys and the gravity surveyors who provide a lot of information so we know what's going on. So the earliest known gravity reading that we're aware of happened in 1819. It was done using a pendulum gravity meter, and that's pretty much what it says on the tin. You time the swing of the pendulum to work out what the gravity is. And that was done by the French. But our story starts in the 1950s. Again, using pendulums from Cambridge, we got a known point, or set up several known points, which then allowed us to use the relative meters to expand the network. And there was also a number of international ties that we've done. There's a lot of international work that we went on early to try and make a global network for gravity. And here you could see Merredin, Western Australia. And we've got diagrams and photos of the location so that people know how to find the place. And you can see it seems pretty good, but when it was visited in 2015, we've had some vegetation overgrowth, which isn't too bad. The site's still there, it's still usable and everything, but you've still got to find it. And one of the other problems that we have is we're now looking in a different direction with the new photo, so we don't know if the hangar is still there. And then we went on to the next step. So more pendulum readings, more international ties, and strengthening of the network. Now, you may notice that it looks like there's a lot of east-west traverses, and that's because there is. As Jack mentioned, there is a gradient from north to south that the early gravity meters actually couldn't utilise. So if you were working in the north of Australia and then went to the South Australia, you had to recalibrate the meters. So what they did is, for the majority, they worked east-west. And here's one of the stations here. This is Ringwood. We think that they actually cleared the land as part of ongoing work, and we took advantage of that, but because there were no landmarks that we could use, we've had to bring our own concrete and make a concrete slab to put the mark on. And when it was visited in 2011, you can see some vegetation there, but essentially it's the same, although we did have to kind of uncover the mark because it was covered in dirt, which made it a bit difficult to find. And then the next swath of work probably completed the first instance of the network. We have a lot of work doing it. As Jack mentioned, we were also starting national coverages for gravity, so there was a lot of assessment of where you could set up camps for that work, and once again, more international ties. Again, here's Anna Plains. The photos give you kind of an idea of where it is, but I wouldn't want to rely on those by themselves. But fortunately, the map, even though it is in imperial distances, does give you a very good idea. One of the other problems we do have, though, is the coordinates that we have for this station aren't really up to today's standards. So, where we can, we put in new coordinates, either using Google Earth or GPS when someone visits the site, and that way it's a lot easier to locate, especially for some things like the windsock has moved or it's been covered in dirt. Then we entered a new phase with a lot more international work in collaboration. We also had a new reference system created that was built on all the work that was done internationally over the last 10 or more years. BMR at that stage, as we were called, also collaborated with the Soviets, who use their pendulum meters to do a number of tests, number of readings. And we also had some more international ties, and as far as we're aware, this is the first time we actually took the gravity values down to Antarctica. One of the stations here is Mount Gungan near Perth. So as Marina mentioned, I've done a lot of data acquisition. I can tell you, standing up to take a reading is a lot easier on the knees. But this is not a place that we would actually want to put a mark these days. It's still there at the moment, but the road's kind of deteriorated and there's new pathways to get there, so we would have to update the maps, probably at a better scale than what you can see here to make it easy to find. And then in the 1980s, again, we started rejuvenating the network. So a lot of replacing old stations and putting some new ones in. During that time where satellites were becoming more important and geodesy was also gaining traction, we put some stations at very long baseline interferometry sites and also laser ranging sites. And here at Yarragadee laser ranging site, you can see us there. You'll also notice that they're in the foreground, someone's taking a gravity reading, hence my comment on the knees. But this is all right site. People there, it's all good, but it's not our site. So they will do the work they do. And of course, over time, they've got new equipment and new trailers, such as the Mobus. So here's our station sitting underneath the trailer pretty much. And that's probably a misnomer because the trailer is now stuck in place. It doesn't move anymore. So from then on is probably the final phase before you use the A10. We did some campaigns every year and took the opportunities by doing other work. You'll notice that Victoria, in the southern part of South Australia, has got a lot of close stations. That's because Victoria at that stage was wanting to cover Victoria in about 2K spacing. So this allowed them to do the work very easily and very quickly of joining everything together. And if we have a look at one of the stations in South Australia, Yantanami, we've progressed to coloured pictures, which is good, but we've also upped the quality of the maps and making it easier for everyone to find. And unfortunately, when it was visited earlier this year, this site was actually shown to be destroyed. So we've lost that, but we've got a number of sites very close by, so it's likely we would not bother to put a new station at this one. And then this is when we started bringing in the A10. So we're now changing from using relative meters to using absolute meters. And we were mostly, during this stage, we were running at established sites. Now this is because we're also developing a new gravity datum, the Australian Absolute Gravity Datum 2007. Plus we're also updating some of our standards and processes. And this is all aimed to make the information you got from the gravity data more useful. Here's the A10 in various sites during that time. You'll notice we are remote in some cases and not so remote in others. And our stations that we were at went from 1950 to 1994. So good spatial and temporal coverage of the data. And that allowed us to make adjustments as we needed. And from then on, we've used the A10, replacing stations, putting new ones in. And usually we put the new ones in because the A10 is more accurate than the meters that we were using previously. So if we take Horse Creek as an example, we put it in 1964. Here's the brass mark that we used at the time. We visited in 2004. You notice that the building slightly changed, but the main part, the concrete, is still there, working good. And then in 2015, we went back, put a new station in. So we've got both stations sitting side by side, separate markers so that you can know which one you're reading. One of the other problems, though, is, regardless of when you're doing this work, is the weather. Have a look at the background. It looks a little bit ominous, and it was. This is probably the worst storm I've ever been in. It was really, really windy and wet. Now I'm going to talk about the A10 itself. So why did we choose the A10? We already had a system that worked. Well, the A10 was more accurate. It didn't have some of the problems that the relative meters had. It also allowed us to visit sites only once rather than multiple times. And you do it multiple times with the relative meters to get a more accurate value. Only having to visit the site once means that the survey length was shorter. There's a couple of caveats though. The time at each site is longer, and some of the criteria of where we can actually take our readings is more stringent than what we used to have. So if we take, as an example, all those stations I showed you from earlier, we could read it one, maybe two, unlikely if we could do the one at Merredin. Mount Gungan on the bottom left is stable enough, but we wouldn't want to lift the A10 up onto that and have it that high. And most of the reasons for not using those other sites is because the A10 needs a firm, solid base to work on. If we look at one of the surveys that we did, say the 1995 Victorian surveys, here's some of the details of it. 14-week work. That's driving most day, well, every day. You're coming into a site several times, usually from a different direction in different loops, because that helps the processing and keeps minimising the errors. But you can see 27,000 Ks of driving in Victoria is interesting, let's say. But with the A10, you're looking at about half to a third of the time. Same for the distance driven. You only visit a site once, so it's a lot easier to plan your logistics. Going on to the A10 itself, 4 main parts. You've got the laptop, which runs everything. You've got the electronic box, which controls the 2 yellow cans you can see. You've got the power supply, which for the most case, because it's mobile, these are batteries. You've got the 2 yellow cans. The top one's called the dropper. The bottom one is called the laser. And everything's connected by cables so the power can run through and all the electronics can talk to each other. Have a look inside the A10. This is a very deceptively simple schematic. So you've got the inclinometers, which keeps the meter vertical as possible so that you get the best reading. You've got the super spring, which keeps everything stable, so movement from the ground or from the machine itself is cancelled out. And then you've got the various other parts that actually do take the readings. As I said, you need power all the time. So the dropping chamber is a vacuum. You've got to keep that in vacuum. You've got to keep the meter above ambient temperature so that there's no heat effects. And of course, you've got to run the electronics. And you've got to take everything with you. So, take a reading. We fire a laser. that laser is split into two beams and hits both these corner cubes and get a reflection. One of the corner cubes stays stationary, so you've got a set distance. The other one in the dropping chamber moves, so that is always changing the distance of the laser beam flows. You then have the beams reflected and they're recombined, but because the reflector in the dropping chamber has changed distance, you get interference when the beams are combined again. This interference, or optical fringes, are detected by the interferometer. And it's that signal that is used to determine what the gravity is. And that occurs once every second, until you get a set. And this is what a set looks like. So each green dot is one reading or one drop. Then I'm not going to go into the stats for this, but you can see it adds them all together, averages them out. There's a standard deviation, so we know how good the reading is. And once you get a number of sets, you can get a value. So here's an example of a good and a bad, but before I go any further, what I'll do is I'll explain why that there's a red and a blue set of readings. The laser has two frequencies, and this is to help protect the laser work. But what happens is if you add both values from the different frequencies together, you get the value of gravity, which is why we always do pairs of readings or an even number of sets. So here you can see the bad readings have got a standard deviation about 3 times of a good reading. And you can see the error bars there showing that pretty definitely. And that is because of the site that we've chosen. So you can see on the left that the site, which is Xanthus in this case, the concrete is old, pitted, there may be cavities underneath. You can also see the windsock, so there's a bit of a wind blowing, hence the tent to protect the A10. Well, on the right, newer concrete, solid base, probably no cavities underneath, and fortunate enough not to have wind. And that is why site selection for us is very important, because you want to get as accurate a reading as possible. And now I'll hand back to Jack.
Okay, thank you, Phil. So yeah, we've heard about what the AFGN is, why we need it, and how it's grown over the years, as well as a bit about the technology that's currently being used to realize it. So for the remainder, I wanted to give a bit of a brief overview of some of the recent work we've done to assess the usability of the network as it is, and work underway and coming under the Resourcing Australia's Prosperity Initiative to ensure it's fit for purpose into the future. So in Q1 and Q2 of this last financial year, GA, working with our external gravity guru, Mark Dransfield, audited the AFGN. We gathered stakeholder input and drafted a revitalisation plan. That review really surfaced 4 key issues. So the first was that the existing infrastructure and database integrity had some issues. The database itself has an automatic site condition field, which sets sites to unknown if they haven't had a recorded visit in 10 or more years. When the network was reviewed, about 200 marks were in a good or okay condition, but the remainder had an unknown status or were destroyed. Also, just due to the vintage of the database, some older marks had coordinates that had been scaled from maps at the time that they were entered into the database, so they didn't always sit nicely on the maps used in the modern data portals. And there were also some kind of metadata inconsistencies. Most of these issues really just reflect the way that the database has kind of grown organically over time. But it's good to use this information and these findings to really set a vision for the future, as well as repair records where we can. The second was stakeholder requirements on the data that we provide access to. There were some recommendations from users of the portal that displaying the site condition and making the metadata easier to understand would really help their use of it. Another key component was the fieldwork logistics. The A10 absolute gravimeter is highly accurate, and it's a wonderful machine, and it's greatly improved the way that we establish AFGN sites, but it's large and it can be expensive to move around and needs dedicated transport. Also, scaling up an in-house AFGN work program would also need at least 2 members of staff out of the office for several months at a time. The final finding was really around the network consistency and standards. So from our assessments, we saw that there's no real consistent single standard governing data collection, the accuracy, or station metadata. So the quality can vary. Again, this is really just a result of the way the database has grown, but it's something that we can fix up going forward. So the next few slides really step through what we're doing to address all of those things. So stakeholder feedback and a look at our field logistics and those that use the network tell us that we really need one reliable benchmark every 200 kilometers. So that number really comes from a gravity surveyor's routine, the ABA tie. Crews need to drive from the survey area to the AFGN mark and back again and repeat that all in one day. So with a 200-kilometer station spacing, the worst case round trip tops out at about 800 kilometers and is just about feasible. We started by asking, how far can the existing network take us? So the dots here are modern marks, post-GPS, where those coordinates have been established in the field with GPS equipment and measured with the A10, and they give us quite a good skeleton. This heat map kind of exposes the gaps in this network, and yeah, the white patches really show where no benchmark lies within 200 kilometers. And for the most part, we can provide the coverage that we need to. However, not every one of these marks is in a known state. 191, the black squares there, needed on-site inspections, while 40, shown by the crosses, are too remote or inaccessible, so they need to be re-established, maybe nearer roads or in towns where surveyors can get to them more easily. So we actually aim to finish all of these inspections and new installations by June next year. GA field crews have already verified about 25 sites whilst they've been out in the field doing other tasks. And yeah, just a big thank you to everybody who's helped there. And in May to June, Zong covered 51 more across WA in the Northern Territory. And Bruce Golby of OPM Consulting added another 50 plus site checks in South Australia and New South Wales while en route collecting AusLAMP equipment. Each one of these site visits also refines site coordinates and metadata with pictures and other information about the sites. So we have the best possible and up-to-date information for these sites to provide to our users. And I'll say here that these early efforts last financial year have drastically cut down on the amount of work needing to be done in this one. So we can really hit the ground running and just stay laser focused on re-establishing those 40 sites which have been marked with a cross there. Fieldwork with the A10 is tricky. There are several requirements and considerations around using it, at least how we've chosen to operate it for fieldwork, and they all add cost and complexity. So for example, as Phil mentioned, it needs to stay powered 24/7, otherwise the vacuum inside of it dissipates. So we need a complex power management plan, even when overnighting in hotels. And it's really a 2-person lift just to move around those 2 cans and the equipment that comes with it. So yeah, we need for a significant step up in the amount of field work that we're doing, we need a purpose-built vehicle that could kind of keep it upright and cushioned and dedicated staff to take it out in the field. So rather than tool up a custom GA vehicle and tie up staff for months, we went to market for a gravimeter operator. We had 3 strong bids that came in, and Daysat Geodetic Surveyors scored the highest during our evaluations, and we've signed a 12-month service contract with them to deliver A10 gravimetry services. The operating model is basically that GA will supply the instrument, training, oversight, and stakeholder liaison, whilst DaSat supplies the crew, custom transport, and all of the field logistics. The work plan itself looks a little bit like what's on the slide there. GA will train selected DaSat staff on safe A10 handling and measurements. Then jointly we'll run potential site assessment checks, go through the land access clearances and final logistics, followed by about 2.5 months of field work, reinstalling those 40 priority marks and verifying the rest of the sites flagged for inspection where practical. The instrument will then return to GA for a lab validation, make sure that we're getting the same measurement, the same number from the device in our lab, where it's been used multiple times, and we'll also QC the data that was collected. We'll then proceed with the kind of the final data processing, and then plug all of those measurements straight into the national database and portal for people to pick up and start using. So yeah, this partnership gives us experienced boots on the ground, and we'll hopefully put every single one of those 40 high priority marks back on the map by the middle of next year. During the consultant review, we canvassed survey companies, state government agencies, and private consultants for feedback on the AFGN. And one of the kind of the more actionable themes was making the portal clearer. So for the portal in the old view, every mark had previously been displayed as a blue triangle, and you had to click each one to sort of learn anything about them, particularly their site condition. And that's shown in the top image there. In the new view, the legend now defaults to site conditions coded symbols, so you can instantly see which sites are healthy, which need to check, or which are retired. We've also removed some cryptic codes. So for example, station type A or B, which was how it was displayed in the previous portal, is now spelled out as absolute or relative observation style, so that users know the quality and type of those measurements. And early feedback has been really positive. We're also actively correcting other metadata fields as the sites are inspected, updating images, and trying to make the information we present as best as we can. I'm sure there's still inconsistencies in records in there, so yeah, we're actively trying to engage with users of the database for any feedback for where this is the case. And if there's anyone watching that has that kind of feedback, there's an email address at the bottom there. The final piece I'd like to touch on is standards and documentation. Boring, but necessary to make sure everything stays on track and is done safely. The first is the data and metadata standard. This is now in draft and being put together with our geodesy colleagues who do similar absolute gravity work. Every future absolute gravity record will be SI traceable, use the same field name conventions, and have the same metadata, and just drop straight into the national database, no matter who collects it. The second is the site selection guidelines, which is a simple, plain English guide specifying things like ground stability requirements, access, long-term security, and things that will just make those sites stand the test of time. And ideally, yeah, if a spot ticks all of those boxes, we hope that we can reoccupy it again in 30 years without any issues. The third is really just some living documents on safe operating. So walking operators through the A10 from that first lift to the final shutdown, using our purpose-built trolley and short hauling and fieldwork risk assessments. And these are things that we intend to update as the fieldwork progresses and make sure that they're kept current. All of this is to make sure we deliver consistent, high-quality absolute gravity data while minimizing the risk to field crews, the instruments, and ensuring that longevity of new installations, just to set us up right for future work. So just as a quick snapshot of how we're strengthening the Australian Fundamental Gravity Network, first, infrastructure and database integrity. We're uplifting the existing network to 318 healthy sites to meet a nearly viable product. Where only about 200 were initially confirmed as good. 191 need on-site checks, and we're making good ground here, and 40 need to be rebuilt. Inspections will kind of refresh site coordinates, metadata where possible, as well as the condition, while new data standards really lock in records to SI traceability and provide uniform templates for new sites. The second is actioning some of that stakeholder feedback. The portal now shows intuitive, color-coded site health and plain language labels. The third is around fieldwork logistics. We've contracted an expert crew to handle transport, setup, and measurement, so we can efficiently install new marks this financial year and finish the much-needed site inspections. And the fourth is just around consistency and standards. Those best practice guides and SOPs will be used to keep every new survey aligned on accuracy, metadata, and WHS. Current repairs will kind of restore that baseline coverage, and next will come targeted infill in remote gaps and really areas of kind of strategic interest. The bottom line is we're fixing the foundation and building a more consistent way to collect gravity data at AFGN sites into the future. A large part of the next steps will also involve lots of engagement. We aim to promote this initiative with as many stakeholders of the AFGN as we can. And I'll be at ASCG in Perth in September to speak to this again. And yeah, again, we'll continue to progress with infill in strategic areas, which we hope will be guided by those conversations with our stakeholders. So just to finish, I've got a few slides on current alternative measurement methods and innovative technologies and the role that the AFGN may play into the future. Airborne gravity is a technique which is now routine for many surveys. Gravity instruments are bolted to an aircraft which flies regular lines to map the gravity field seamlessly on and offshore or over large distances. And I suppose importantly, it takes weeks rather than months. Compared to terrestrial boots on the ground methods, the data offer a kind of comparatively low cost, passive, non-invasive peek at the subsurface over very large areas. And there are really kind of two flavors, scalar and gradiometry. Scalar airborne gravimetry senses the pull of gravity as the instrument flies along the flight path, and it really resolves kind of kilometer scale features. However, these instruments are still relative, so every campaign needs to tie off to at least one AFGN benchmark so that the data can tie into the national datum, particularly important if we want to be able to use those data sets seamlessly with our existing data holdings. Many AFGN marks have actually been installed near airports or on runways themselves for suppliers of this sort of data to be able to connect to the gravity datum easily, and we suspect there'll be a need to do this more into the future, for these kind of broad-scale surveys. The other technique here is gravity gradiometry. This differs a little. It measures the gradient of gravity, which is kind of like two gravity measurements together, the baseline between them, and you're capturing very small differences, but it can see features down to about 150 meters. The raw gradients themselves don't really need an AFGN tie, and in principle mesh together seamlessly. These sorts of data are becoming very commonplace, and the data can be readily ingested by many geophysics software packages, sort of as is. However, it's often helpful to look at gradiometry data alongside regional data, which kind of provides that broad scale of the kind of the context of the geology. So to do this, the gradient data are mathematically transformed into more conventional gravity data and blended with existing data sets. So the AFGN will continue to have a role in underpinning this sort of regional scale information. So to best serve these use cases, we should aim to strive to provide access to the gravity datum at airports and facilities used by airborne gravity operators. We're also tracking emerging absolute gravity technologies and operating models that could reshape how or whether we continue to rely on the AFGN into the future. One of these technologies is miniaturized free-fall meters, which are in early development and promise to shrink the classic mass-dropping type gravimeter into a box not much larger than today's relative gravimeters. early results look really good, and these instruments might find applications in tying scalar airborne gravity data into datum, or even topping up relative surveys on the fly without needing to drive those long distances out to AFGN sites, which could be an incredible advancement. This is something the ANU are working on, and yeah, we're really excited to see how this progresses. Quantum gravimeters are also making their way to market and being used. These use quantum techniques like cold atom interferometry to measure gravity and can reach microgal precision. Commercially available units now match the A10 accuracy, but most are still A10 sized, like the one shown there on the left. So they really do require similar logistics and considerations, much like the A10 does. Smaller ones are on their way to market, and there's an example of one there on the right from Nomad Atomics. And yeah, others have kind of just begun delivering these quantum absolute gravity data as kind of as a data as a service type operating model, where you might purchase the data or the measurements rather than the hardware itself. That can be attractive as it would remove the costs involved in operating our own instruments, and we really hope that the data standards we're working on can support these groups and ensure consistency across data products. We're watching this space, and yeah, we're really excited to see data from surveys like this into the future. So yeah, we're keeping abreast of all of these developments, but in the short term, the A10 remains the backbone of the AFGN work. And even with all of these technological advancements, we still anticipate that the AFGN has a 30-year useful lifespan until these alternatives are commonplace and traditional relative gravity surveying is completely superseded. So just to finish, the AFGN is what makes regional to continental scale gravity mapping possible, and we're giving it an uplift to make sure it serves stakeholders better. We're revitalizing the infrastructure that we've already got and pushing ahead with cost-efficient and cost-effective ways to establish new sites. As the RAPI project progresses, we'll focus on infill of this network shaped around users' needs and plugging holes in the existing data coverage. RAPI will support around 30 to 40 new site installations per year until we meet our objective of providing an updated realization of the AFGN before 2032. And just as a final note, if anybody watching has an upcoming gravity survey or is visiting an AFGN mark, please do reach out. Updated site information is gold dust, and we greatly appreciated it. And yeah, please let us know if you've got new work areas where we might be able to do some kind of strategic site installations. Feel free to get in touch via that email, and one of the Gravity team will get back to you. Thanks.